Problems in Fluids 2, problem number 6. In the drawing to the right, the pipe is used to pump oil which has a density of 0.8 grams per cubic centimeter. So that's what we call rho. Oil flows into the larger pipe at 3.45 meters per second. The input pipe diameter is 65.5 centimeters, so that is 32.75 centimeters radius. The diameter of the output pipe is 5.52 centimeters, so the diameter or the radius of the output is 2.76 centimeters. What is the velocity of the oil exiting the smaller pipe? I'm going to call the smaller end number 2, and I'm going to call the larger end number 1. First of all, whatever volume flows in here must come out here. So we have what is called the continuity equation. The area at 1 times the velocity at 1. Velocity, remember, is meters per second, so it's meters in this direction. If I multiply that by the area, I get the volume, so that's the volume flow per second. That has to equal the area at 2 times the volume at 2. So I have the velocity at 2 is equal to the velocity at 1 times the area 1 over area 2. That's equal to 3.45 meters per second. Now the area is going to be pi times the radius squared. So the radius here is 32.75 centimeters squared. This area is going to be pi times 2.76 centimeters squared, pi r squared. The pi's cancel out. And this is equal to 4.86 meters per second. So the next part of the question might be then, what does that say about the differential pressure? Differential means difference. So the difference at P1 versus the difference between that and the pressure at P2. What is that difference? Now let's look at how to find the pressure differential. Bernoulli's equation says the pressure at 1 plus rho g H1 plus 1/2 rho V1 squared, where V is the velocity, is equal to the pressure at 2 plus rho g H2 plus 1/2 rho times the velocity at 2 squared. Let's look at the equation for a moment. This is a conservation of energy equation of sorts. Here is the potential energy, rho gh. Here is the kinetic energy, 1/2 rho v squared. Rho, remember, is the mass density, so this is like the mass, but it's a density. This is a little bit different though, and we have P1 and P2, so it is not exactly a conservation of energy equation. But the Bernoulli equation is very much an energy type description of what's happening to the water. So let's see what's happening here. Let's pick H1 here, this top height. Let's pick that to be 0. So I then do not have this term here, and then I only have the difference in height here, which is given as 14.3 meters. Down here, that's going to be a minus because it's actually now measured from 0. Watch the signs. So now I have the pressure differential, which I have P1 minus P2. That is going to be equal to rho g H2 plus 1/2 rho V2 squared minus V1 squared. This becomes 800 kilograms per cubic meter, 9.8 meters per second squared, and H2 is a minus 14.3 meters. That will be plus 1/2. Rho is again 800 kilograms per cubic meter. And now I have the difference in velocities. So I have 4.86 meters per second, that term squared, minus 3.45 meters per second squared. This is equal to minus 1.12 times 10 to the 5th pascals plus 4,686 pascals. And so my answer is 117 kilopascals. When you work problems like this, watch these signs, because that gets subtracted from this portion of it. So be careful about the signs. When you pick this to be the elevation, then H2 gets a negative sign.